How much energy is needed to convert 100 grams of ice at negative 23 degrees Celsius or negative 20 degrees Celsius to steam at 120 degrees Celsius? First note, you need an amount of ice because the more ice you have, the more energy that will be needed. So put in 100 grams there. I don't think that's on your sheet. It looks like I see an answer here, 73.8 kcal, which stands for kilocalories. Let's look at how we're going to get to that. We're going to start with ice. We're ultimately going to heat up the ice, then convert it to liquid, then heat up the liquid, convert it to steam, and then heat up the steam to 120 degrees Celsius. And we're going to need to add up all those components. Let's take a look over here. Here is a chart or diagram that you have, and I don't think I labeled the axes with the temperature in degrees Celsius, and then just over time to the ice we're adding heat energy right here. But when we start with ice, let's just look at phases right here. Between point A and B, we have ice. Between B and C, we're converting that ice to liquid. It's melting. Notice the temperature stops as the energy is going to be used to make the change of state happen. Between C and D, the temperature rises as the molecules slide over each other faster in the liquid state. Between D and F, the temperature levels off as it goes from liquid to gas, taking potential energy to change from a liquid to a gas, separating the molecules of H2O from each other. Once it's all converted to gas, then the temperature will rise up as the molecules move around even faster in that gaseous state. So let's just look at a couple molecules here, and we have a couple liquid molecules. Okay, wow, these are big, okay, right here, and they're kind of vibrating when they're in the solid state, and they're sliding over each other when they're in the liquid state, and in the gas state, oh, there they go, they're separating away from each other. Okay, not only when you do along the plateaus, what you're seeing is sliding over each other faster or moving faster along the phase changes, the energy it takes to like separate or break away from each other. Let's take a look at the mathematics behind this. Let's just look at this overall. From A to B, it's 1 kilocalorie. From B to C, it's 8 kilocalories. From C to D, it's 10 kilocalories. From D to E, it's 53.9 kilocalories. From E to F, it's 0.9 kilocalories. So the biggest amount is in this phase change going from a liquid to gas where the molecules have to separate from each other. Let's look at the specifics on how we'll do this. I'm going to sneak over and look at page 2 of your homework packet where you have some formulas, and it's right here. And we got a definition of a calorie, which is the energy needed to raise 1 gram of water by 1 degree Celsius. That's the definition of a calorie. Your book will probably use joules. Essentially, if you know that for every 1 calorie, there are a little bit more than 4 joules, and you can make those conversions. Okay, coming at it from a physics point of view, it probably makes more sense to use joules, but this will be okay for us. Just to note, a food calorie, food gives you energy. A food calorie is actually a kilocalorie, or 1,000 calories. There's 2 main formulas. One is the plateau formula, and one is a slope formula. We're going to start with the slope formula, which is down at the bottom, which is down here, and you're going to see energy equals Cm triangle T, where C is the heat capacity of water and the heat capacity of a substance. For liquid water, it's 1 calorie per gram degree Celsius. For ice, it's 0.50 calories per gram degree Celsius, and for steam, it's 0.45 calories per gram degree Celsius. M is going to be for mass, and triangle T is the change in temperature. Let's take a closer look at our slope formula and see if I can get connected here. I think I can. here. Okay, let's try this right here. So energy equals Cm triangle T. When I'm going from A to B, I'm actually going from -20 to 0 degrees. So there's a 20-degree temperature change when I do that. Okay, the heat capacity for ice is 0.50 calories per gram degree Celsius, and I have 100 grams of ice. Notice I multiply these things together. That gives me 1,000 calories, which would be 1 kilocalorie. The next one is going from C to D, which is really going from 0 to 100, which is 100-degree temperature change, again 100 grams, but I'm going to use the heat capacity of liquid water, which is 1 calorie per gram degree Celsius. And the last one is going from E to F, which is going from 100 to 120, so it's a 20-degree temperature change, it's 100 grams, and the heat capacity of steam is 0.45. Notice these are all in calories. I convert them to kcals, and essentially I get 1 kcal, 10 kcals, and 0.9 kcals. The next formula we want to look at is the plateau formula, sometimes called the latent heat, because it's not reflected in molecules moving faster, but a change in potential energy or a change in position. And it's N, which is the number of moles, times delta HF if you're on the lower plateau, which is the molar heat of freezing or fusion, and N equals N times delta HV, which is a molar heat of vaporization. Condensation would always fit there. So notice my delta HF is changing heat content, or you could call it the molar heat of fusion, which would be freezing or melting. And delta HV is a change in heat content for H2O, or the molar heat of vaporization or condensing. Notice vaporization and condensing have the same amount of energy, but opposite signs. Freezing and melting, same amount of energy, opposite signs. I figure out my moles, 100 divided by the molar mass, which is 18, and I get 5.56 moles. And then I look at my formula guide, and I can see, oh, I just need to plug in, molar heat of fusion is 1.44 kcals per mole. Molar heat of vaporization is 9.70 kcals per mole. So for the lower plateau problem, I plug in, and we'll see if we can see that here. 1.44 kcals per mole, I get 8.0 kcals. And for the other one, I plug in 9.70 kcals per mole, which I get 53.9 kcals. Notice the vaporization one is what, 6-7 times higher than the fusion or freezing melting one, because you have to completely separate the H2O molecules from each other, which takes more potential energy to do that. What am I ultimately going to do when I have all these energies in our graph that we can see right here? I take the 1 and the 8 and the 10.0 and the 53.9 and the 0.90. I add them up and I get 73.9 kcals. That's the amount of energy needed to convert 100 grams of ice at -20 degrees Celsius to steam at 120 degrees Celsius.